So, hello and welcome back for Lecture 2, Part 2. In Part 1 we discussed fusion and introduced you to the basic material requirements when looking at material selection for nuclear applications. And in Part 2 we'll begin to look at the components of a nuclear fission reactor and review some of the most prevalent reactor designs from the world's first ever commercial nuclear power station, which was built in England in 1956, to the proposed next generation of reactors for the future. So, if you jump back to page 18 of your notes, which I show here, you'll see brief summaries of the key components within fission reactors in terms of their function and their material considerations. And first and most importantly, you're going to have the nuclear fuel itself. And that can be metallic, alloy, or in ceramic form, as we'll see later on in the course. Uranium oxide, which is a ceramic, is the most common, and we normally use that with slightly enriched uranium. Enriched uranium meaning enriched in uranium-235, a fissile isotope. And that fuel is going to be covered in a cladding. So that's the cladding, and that provides structural support to the fuel and prevents fission products from contaminating the coolant outside the cladding, whilst protecting the fuel on the inside from corrosion due to that coolant. So you've got your fuel, and that's clad in cladding, and then outside your cladding, if you've got a thermal reactor, you're going to have something called a moderator, which I've mentioned before. And the function of a moderator is to slow down neutrons in order to increase the probability of a fission event occurring. Because as you'll recall, neutron cross-section is a function of neutron energy. I showed you a graph for uranium-235, showed with a higher likelihood of fission occurring for neutrons of lower energy. And we depend on that slowing down of neutrons to really sustain a fission reaction in thermal reactors. So what's a moderator made out of? Well, graphite is a possible moderator that's used in gas reactors, as I'll show in the next part of this lecture. Or you can use your coolant as a moderator, such as for light water and heavy water reactors. So light water and heavy water are the moderators and the coolants. But some reactors, such as fast breeder reactors, they're fast reactors and they don't require moderation, which is something I'll cover towards the end of this lecture. But outside of your moderator, fuel, cladding, moderator, then you're going to have a reflector. And that's pretty obvious what it does, exactly what it does on the tin, or says on the tin. It reflects leaked neutrons back into the core. You might also have some shielding, which again is fairly straightforward in its function. It shields the components on the other side of the shield from radiation. You might want to do that because you've got certain sensitive features, such as welds on the pressure vessels, that are more susceptible to radiation embrittlement. And that pressure vessel that I mentioned, that has a very important job, because, for example, in a pressurized water reactor, it's quite a pressure in there, and the pressurized vessel is the pressure boundary containing all other key internal components. And as the most common type of reactor is a pressurized light water reactor, that vessel has to withstand those pressures and maintain its structural integrity throughout its design life. So those are the key components of a fission reactor that we will look at throughout this course. There are, of course, other components beyond these, but I leave those to your own private reading, should your curiosity obligate you. Right, so let's hop over now to page 21, and we can start putting these components together to see some, sort of real reactor designs. And the figure that I show here presents the timeline of the different generations of nuclear reactor. From the first generation right through, so the first generation would be the UK's own Magnox reactors, the last of which was retired in 2015. The Generation 2 reactors, which make up the majority of currently operating reactors, and the Generation 3 and 4 reactors that show improvements in performance and safety over the current generation. With Generation 4 reactors expected in the next few decades. It's unlikely it will occur before within the next few years. So let's begin with the first generation reactors. What did they look like? Well, you will be pleased to hear that the world's first ever commercial nuclear reactor was built and operated here in England, at Calder Hall in Sellafield, which is in Cumbria. And that began operation in, I think, 1956. I think it says it in the, there you go, 1956. It was one of 4 Magnox reactors built at Sellafield, known as Magnox on account of the cladding that they used. It was magnesium non-oxidizing alloy, so Magnox, non-oxidizing. That was used for the fuel cladding. It was an alloy principally of magnesium, aluminium and beryllium. The magnesium, because it has a very low thermal neutron capture cross-section, which is just what you want from a cladding, as we saw in the last lecture. So that helps your neutron economy. And the alloy proved to actually be quite creep resistant. So it was a very positive alloy to use. And it was quite resistant to the CO2 coolant used in those reactors, which are known as gas reactors. CO2 in gas form, gas-cooled reactors. And also it was quite unreactive with respect to the uranium. It was actually cladding, it was holding. And they added the aluminium and beryllium to improve strength. So he gets some solid solution strengthening, and the beryllium helps oxidation resistance. And the Magnox, the reactors proved extremely useful to the UK in terms of their weapons program, because they were principally used for the production of plutonium for our weapons. And that's produced through the transmutation of uranium, and it can be obtained from partially used nuclear fuel. So actually a modern commercial reactor actually produces more energy from plutonium at the end of its life than uranium. But you can, early on in the life, you can switch off your reactor and get that fuel and take that plutonium and enrich it to have weapons-grade plutonium. And I've provided a schematic of the Magnox reactor here. So, as you can see, you have carbon dioxide coolant that is circulating up through channels in the core, increasing in temperature as it does so, taking away the heat from the core produced by the fission, takes that heat and passes it through heat exchangers, where it's transferred to the heat exchanger tubing. And the tubing is shown here with blue and red. Those colours signify the temperature of the water contained within those tubes. And that section is called the secondary circuit, because in our primary circuit we've got CO2 coolant. In our secondary circuit, which is isolated, it's water. Well, why? Why would you want water? Well, the heat produced in the core and carried by our CO2 coolant must be used at some point to heat up steam to run a turbine that turns a generator and in turn makes electricity. So this secondary circuit is where that steam is produced, which itself is circulated through the secondary circuit. Why CO2 as the coolant? Well, carbon dioxide, CO2 absorbs less neutrons than water. And when used with graphite as a moderator, and the graphite are the grey bits surrounding the fuel rods in the schematic, so that's the moderator. So you've got the CO2, it allows the use of unenriched uranium because of that improvement in the neutron economy. And that was extremely useful in the UK's pursuit of nuclear weapons, because you didn't need to have enrichment facilities. You could produce plutonium using just natural unenriched uranium. So because of that prioritisation of plutonium production, those reactors weren't particularly efficient because they ran at relatively low temperature and had rather poor power capacity, meaning that the more modern gas reactors far exceed these in efficiency, because a lot of this technology, as I'll show you, is used in the advanced gas reactors. So these were the babies for our advanced gas reactors. Now if you look at that schematic, you'll be able to spot the control rods that enter the core from the top of the reactor. Why do you think control rods entering from the top is a good idea? Well, control rods can shut down your fission reactions. Yeah? They control the reactions. So should you wish to do that in an emergency, for example, having gravity on your side is pretty useful. So, because one way of moving control rods is with electromagnets. So should you lose all power, those magnets will demagnetize and no longer hold the control rods in place. So the rods would fall into the reactor by gravity. There are alternative ways of entering control rods. They can be fired in using a pressurized gas system, and I'll show you that for the advanced gas reactors. And that just ensures they shut down their reactions as quickly as possible. So that's a big advantage. You want those control rods to be fired in. And most reactors following these first reactors hold a lot of similar design characteristics, but can differ greatly in others. Because as I mentioned, most commercial reactors today are light water reactors. And of light water reactors, there are two types. There are boiling water reactors and pressurized water reactors. Now, pressurized water reactors, also known as PWRs, they make up around 65% of the total operational reactors across the world, with BWRs being around 21%. And then you've got heavy water reactors, which I'll cover later. They're about 11%. So it leads that we should probably focus on pressurized water reactors first, given their abundance. So let's have a look. How does a typical PWR differ from that of a Magnox reactor? Well, if you look at the schematic I've provided here on page 23, you'll see that a PWR has two separate loops. You've got the primary loop, which is pressurized to around 15 megapascals, and that's done to prevent the water from boiling, even at its operating temperatures of around 320 to 350 degrees Celsius. And then you've got the secondary loop, and that secondary loop runs at a lower pressure to allow the formation of steam to run that turbine. Now, if you look at the primary loop, within the primary loop is the reactor core, which is contained within a pressure vessel, and that pressure vessel is made of low alloy ferritic steel. They're typically around 12 meters in height, 5 meters in diameter, to give you a perspective. Of course, you might be thinking of ferritic alloy, low alloy steel in contact with water. What about the rust? Well, the interior of these aren't going to rust because we clad them in stainless steel and or nickel-based alloy to provide some corrosion resistance. So that solves that issue. But within the core itself, let's think about how we're going to form our fuel. How is this fuel placed? Well, you have things called fuel assemblies. And fuel assemblies contain fuel elements. And a fuel element contains slightly enriched uranium dioxide pellets. They're little pellets, and they're stacked up on top of each other. And those pellets are clad in a zirconium alloy, which again I'll discuss later on in the course. Now typically you would expect a fuel element to hold around 200 of those rods, individual rods. So a fuel element has about 200, and in a core you'd expect around 180 elements to form that whole reactor core. So it's a lot of fuel rods. And within those elements, you've got channels for the coolant to travel to get that heat out of the fuel. And in this case, we've got light water. And in this case, light water also serves as our moderator. So light water is the coolant, but it also slows down the neutrons to allow fission to occur. You're also going to have channels for the entry of the control rods. And those control rods are typically silver, indium, cadmium alloy, or they can be boron carbide, and they're clad in, for example, stainless steel. And we'll talk about control rods again in more detail later on. So let's get back. We heat the water in our primary circuit through the core as it's pumped around through to that steam generator. You see in the schematic the steam generator, all of which is within a reinforced concrete containment structure as shown in the schematic. And that containment structure protects the reactor from the hazards of the external environment, such as external missiles, planes crashing into it, for example, but also prevents the release of radioactive material that is contained within the structure should you have a leak. Now, if you look at the steam generator, in a similar fashion to our Magnox reactors, the PWRs have water that's circulated across thousands of tiny steam generator tubes. And those tubes are typically made of a nickel-based alloy called alloy 690. And what these tubes allow is the transfer of heat from the primary circuit to the lower pressure secondary circuit, where steam is raised, which follows round to a turbine, just like in a coal plant, which is attached to a generator which produces the electricity that we can then distribute across the electricity network. Now, once the steam has passed through the turbine, it's got to be condensed. And it's condensed using a tertiary loop of cool water. In most cases, this is provided by seawater. That's why you've got nuclear plants next to the sea. And it's pumped back to be heated up again in the secondary circuit. The water is pumped again to be heated up in the steam generator, and it goes round and round and round. So the cooling towers that you see by reactor plants are linked to those tertiary condensers. That's where the tertiary loop cools the secondary loop. So it's not pollution that you see rising from those towers, but water vapour. Okay? Because they are where the water is being condensed. So why have a secondary loop and a primary loop? Why have we got these two different circuits? Why not just have steam form in the primary circuit and save yourself the effort of having a steam generator? Well, some people do that. This is what we do in boiling water reactors. And that has both advantages and disadvantages, as we'll talk about now. Now, a boiling water reactor is quite similar to a PWR. Has a reactor pressure vessel. However, the key difference is that loop design, that single loop design, with the light water running at a lower pressure in that loop of around 7 megapascals. So that is a low enough pressure that the water can boil within the reactor core. And in turn, it produces steam of around 290 to 330 degrees Celsius. Again, these reactors use slightly enriched ceramic uranium dioxide for the fuel and are clad again in a zirconium alloy cladding. But BWR core designs are quite different. For example, they contain about 800 fuel assemblies with around up to 100 fuel rods per assembly. So a lot more than in a PWR. But the advantages of a PWR are as follows. Having a single loop allows you to run at lower pressures, which means that it reduces the stresses on some of your components. And so, in turn, you're going to reduce the risk of those components breaking or rupturing. Higher pressure is going to make you more liable to rupture, isn't it? And that risk of rupture is further reduced because you've got less piping. If you've only got one circuit, you've got much less pipe length, so less pipe to rupture. Furthermore, you can operate at lower nuclear fuel temperatures, due largely to heat transfer by latent heat of vaporization, which is what you get in the core of a BWR, rather than sensible heat in a PWR. We don't need to go into the nitty-gritty of that. But BWRs can operate at lower core power as well, using natural circulation. So they don't need forced flow. That's a positive. You can turn off these circulators, or pumps rather. Not only that, you can have fewer components because you haven't got your steam generator or your pressurizer anymore, which is used to pressure the primary circuit in a PWR, among many other unique advantages. Of course, everything that has its advantages has its disadvantages. There's a reason why PWRs are so popular. BWRs are more complex to manage in terms of their consumption of nuclear fuel, because you've got that two-phase fluid flow in the upper part of the core where you're starting to produce steam. So you've got two phases. And that's going to require instrumentation as well to monitor that two-phase flow. So that's a lot more complicated. Not only that, but you need a larger pressure vessel than you do in a PWR for the same amount of power. And that's going to cost more. And of course, probably you've thought of this yourself, if you only have one circuit, you're going to contaminate your turbines with short-lived activation products. Meaning that in order to run these safely, these turbines, you're going to need shielding around those, because you've got radioactive steam travelling from the core right through to the turbine, which you wouldn't have with a PWR, because you've got two separate loops. I mean, it turns out that's a minor concern, because nitrogen-16 is the key element there, and that only has a half-life of around 7 seconds. So the turbine chamber, you can be entered within minutes of shutting down your reactor. But there's one other thing that you might have spotted if you look at the boiling water schematic that I've given you. Something to do with the control rods. How they're inserted? Well, they're inserted from below the reactor, meaning that gravity is no longer our friend. So no electromagnets here. We rely on dedicated high-pressure hydraulic accumulators, and the pressure inside of the reactor pressure vessel as well to force the control rods in. It's getting a bit loud outside. So that's PWRs and BWRs. But you might be thinking, well, Magnox, you said the last one was ended in 2015. Well, did CO2 coolant die with the Magnox? No. What we have is advanced gas reactors. Okay. So advanced gas reactors are based on the fundamentals developed in those early gas reactors that have been developed into the sort of UK's pride and joy that is the advanced gas reactor. And there are 14 of those operating, all of which are in the UK. Okay. They're much better in terms of thermal efficiency in comparison to PWRs, mainly due to the temperature difference between the steam and the cooling water. And these run at a much higher temperature than the old Magnox reactors, so that's going to also improve thermal efficiency. That was one of the main limitations of the Magnox, because they were worried about reactions at higher temperatures. Another key benefit is they use identical turbo generators to conventional coal-fired power plants, meaning that you can use identical tried and tested turbo generator plants in these reactors. But instead of zirconium cladding here, we use stainless steel. And instead of water being our moderator, we use graphite, just like the Magnox. So you can see that they've used that basic technology to develop these advanced gas reactors. And in the schematic that I've given you, you can see you've got a concrete pressure vessel around the core and the heat exchangers, all within a single pressure vessel, which is different to what we've seen before. Again, it's like the Magnox, but it's different to our water reactors. But we use water in the secondary circuit, like our other reactors, with CO2 as just the primary circuit coolant. So really, those are the most prominent Generation 2 reactors. There are others, such as the CANDU reactor. So I'll just talk briefly about the CANDU reactor and the key advantages. They're called CANDU because CANDU basically stands for Canadian Deuterium Uranium Reactor, which is essentially a pressurized heavy water reactor. And you'll remember, now I've mentioned heavy water, you remember that the use of heavy water negates the necessity to enrich your fuel. And that allows operators to use natural unenriched uranium, which is extremely useful if you don't have fuel enrichment capability. The reason? Well, you can do that because deuterated water, heavy water, absorbs less neutrons, which means that you have more neutrons available for your fission reactions. On top of that, CANDU has an advantage that it affords your operator to refuel without shutting down the reactor. It's quite useful, so you can have constant, continual operation of your reactor because they can depressurize certain channels and remove the fuel as the reactor continues to operate. And that's unachievable with our PWR designs. I think it's still right. All in all, there are about 32 CANDU reactors across the world, such as in Argentina. So it's been quite a successful Canadian export. They don't just have maple syrup. So all the reactors that we've covered so far have been thermal reactors. But I've mentioned before that some reactors don't require a moderator, and they're called fast reactors. Or you may hear them being called fast breeder reactors. So called because they actually produce their own fissile material in the fuel, as we do in all commercial reactors, but a breeder reactor is one that produces more new fuel than it consumes during its operation. It does this by converting fertile material into fissile material, such as transmuting uranium-238 to plutonium-239. Uranium-238 is fertile, plutonium-239 is fissile. And that's a reaction that occurs in all commercial thermal reactors, just not to the same extent as in a fast breeder reactor. Although it is worth noting that most commercial thermal reactors produce more power, in fact, from plutonium fission than uranium when they're at the end of their lives, because you've produced all that plutonium, so that's the main fissile fuel that you're burning up. Now, fast breeder reactors most commonly use a liquid metal coolant and have a much higher power density due to the lack of moderator, meaning you can pack more fuel into a smaller space, with higher temperatures being reached, producing better efficiency. Of course, like any other reactor, they have their own unique issues. Sodium is the most common liquid metal coolant used, and sodium reacts quite readily with water and air, and also becomes radioactive as it passes through the core, so they become quite significant safety concerns. So that's our main reactors, really. There you have it. These are the reactors we have to choose from, with modern generation 3 and 4 designs being based on these that we just covered, but with improvements in safety, efficiency, having longer lives and greater capacities, for example. But the material challenges remain the same. So let's take a miss on those generation 3 and 4 reactors and get stuck into some of the material science. And so, next lecture, we'll do just that. We'll look at the fundamentals of radiation damage, from displacement cascades to the formation of voids and dislocation loops, before we move on to look at component and material specific events. So it's going to be our last hog through the fundamentals before we start to look at the component and material specifics. So I hope you found this lecture interesting. And again, should you have any questions, drop me a comment, and then we'll get started on the next chapter of the course. So I hope you've enjoyed it. Thanks very much.